Okay, welcome all of you for the third section. Here, as you guys told me in the last class, I have introduced more questions so that we get a continuous feedback on what is happening. And then I have some surprise also, because based on the feedback I made it ready something I will tell you later. Okay. So let us first go through what we have done yesterday, some questions on that. Okay. So if you can respond faster, we can move faster. So please, do not take more time to answer. I want at least 80% of you to answer the question. I want 100%. Why 80%? I want 100%. Each one of you should answer. Even if it is wrong, no problem. Try your best. Okay. Anyway, in the exam, you have to make a choice. Think like that and try to answer everything. I want 100%. Then we can go forward. If you answer fast, we can go fast. Okay. So let me put the first question. I need to, okay, look at the question first. I will launch the poll. I'm sure some of you can identify which car manufacturing company it is.
Audi.
Okay. I'm sure EC34 will be, I don't know whether he is there. He is the fan of cars. Okay, let me launch the poll. Okay, sorry. Sorry.
The answer is yes, sir.
I'm sorry. Can you tell me?
We saw the answer.
Oh, you got the answer. Okay.
The answer is shown on the screen.
No, 1 second. Okay, very good, 100%. So thanks for sharing. So I am sharing the results. Now I am worried whether my answer, what was that? So let me check it. Very good. So how did you find out?
I just saw your.
The answer you saw?
Yes,
Yeah.
we saw the answer.
Thanks for being frank. Okay, let me explain the answer. See, CC is, okay, you see the answer, MISD. A car is a single unit, a data we can consider to be single data, but at every stage, different operation is done on it. One guy will do the painting, one will fix the seat cover or brand headlights. Like that, actions are done on a particular element. So we can consider it to be an object or a data where multiple instructions are getting operated on, getting executed on. So MISD is the right answer. Hope you are not seeing the next question. So let me stop sharing this and then let me show the next question. Can you identify the airport? Which city it is?
Yes.
Which one? I will give a clue. It is in India.
Bangalore.
Very good. I am not sure whether those three guys identify it. Okay. So let me launch now. So let me give a clue. From the airline staff perspective, I want you to answer, okay? What do they do? they do something on the passengers, in the sense with the passengers they do something. So how do you map it to a CPU? Here the CPU is the airline staff. Okay, while you are answering, let me ask a question. Do airline staff do different things for different passengers? They have a set of things to be done, especially they ask you for a identity, you will share the passport, then they'll ask you to give the ticket, then they issue a boarding pass, and all of them do it in parallel, and they all do same thing which they have been instructed to do. So in that case, are they executing single sequence of instruction or multiple instructions? See, they are executing sequence of instructions, but are they doing the same sequence? Okay, they are doing the same sequence of instruction. Are they doing it on the same set of people or different people?
Different people.
Yes.
Different people.
In that case, what should be chosen?
B.
But there are some answers showing C and D. Can you change?
B.
Still, I think you can change, but no, I think you can change it if you really understand it. Otherwise, you can still say I am still thinking that it is some other thing. So SIMD is the right answer. Okay, it depends on what we call. Okay, we are making the airline staff as a CPU, and what is it doing? It is executing some set of instruction on different data in parallel. They're all doing it in parallel. Multiple passengers get checked in simultaneously. All those airline staff perform the same job. So that is the answer, but still some people are not ready with the willingness to change the answer. Maybe you thought this is the answer and then you don't want to change it again. Is it clear?
Yes.
Okay.
Yes, sir.
Okay. So let me stop sharing. Okay, guys. This is little more difficult. Take your time. Let me give more data. I will help you in doing it. First read it. Okay, let us solve it while I will not share the answer. I will only explain the question and then I want you to answer the question. So right now, let me explain the question. I showed you the picture yesterday also. This is a multi-core processor having 3 levels of cache. And from the size of each cache shown, you can understand that their total cache size is different. And it is written here, it is 32 kilobyte each. This is 256 kilobyte and this is 2 MB. This is the total size of the cache. Okay. Now I am giving you one more input here. All 3 caches have the same block size 64 bytes of 64 bytes. What I mean by that is when cache is trying to access something from the memory, okay, when I say cache, it is because of some CPU instruction accessing some data in the memory. Okay, it is not that cache is doing it on its own. Cache is just lifeless as SRAM for storing data. That's all, code or data. It is initiated by the CPU. CPU is executing an instruction because the instruction is residing in some location. It wants to access that instruction. While accessing that instruction, suppose if it is a 4-byte instruction, because all the RISC processors, 32-bit processor, have 32 bits of instruction. So every instruction is 32-bit wide. So it is trying to access 4 bytes. Assume it is a instruction or data. Here I have given it to a data. The same logic holds good for both. Do not worry about whether it is accessing a instruction or data. It is trying to access some 4 bytes. Either it could be code, which is an instruction, or it is a data, which could be some variable or array element or whatever. So how does the CPU access it? It is accessing it either through giving the PC program counter value, which is a address in the program memory to access an instruction, to fetch an instruction. If it is doing a move or load or store, LD or store, then it is accessing a data. So while it is accessing just a 4 byte, normally cache will access the block size, whatever may be the block size, it will read always that much of data or code from the memory, because of locality of reference, it is going to be used. CPU may need the next byte or next word in the next cycle. So it is better to fetch something around the bytes, so that later on it doesn't have to go to the memory, it can get it from the cache, which is faster. Going to the memory is much slower. So if the CPU asks for 4 bytes, it will get 64 bytes into the cache. Now, I will not give you more data, more information to answer the question. I think this is enough. Okay, let me give you more. When I say all 3 caches have 64 byte as a block size, means this cache also, though size is 2 MB, it can hold so many 64 bytes of blocks. Okay, 2 MB by 64 is the number of blocks in the cache. Here it will be less, because total cache size is little less than the 2 MB. So here also the block size is 64. Similarly, this is also block size is 64. Okay, this is another input based on this line. Now what am I asking? I am saying that an address at 1000 means it is aligned to 64 bytes. That means if you divide this by 64, you will get a remainder as 0. So it's sure to be aligned. That means if it is asking for 4 byte, it is the first 4 byte in the block. The CPU is asking for the first 4 bytes of a 64 byte block. So it may ask remaining bytes in the same block. So that is what this line states. Okay. So it is asking for 64 bytes starting from address 1000, and it's a data. Okay. Now, what am I asking? If it is asking, it is accessing this address for the first time. That means what? This particular address 1000 and 64 byte from 1000 has never been accessed by the CPU earlier. That means this block is not here, it is not here, and it is not here also, because this is a data cache. I said it is a data array. So this 64 byte of data never accessed by the CPU earlier. That means this is not available already. That means what? It's not going to have a hit, cache hit, either here or here or here. It is going to be a miss always, all through. So let me explain one more thing. When the CPU is accessing a data, it will first check whether it is there in L1. If it is not there, it will check whether it is in L2, because it has more number of blocks it can store. So it might be having that data block here. If it is not here, it will check whether it is available in L3, because it has got much more number of blocks it can hold. So if it was earlier accessed, it may be available here. Now I am saying it is accessed for the first time, so it is not likely to be available in anywhere. Okay, this block is not accessible. I'm just saying that it is not there anywhere. So it has to get it from main memory. What I want you to answer is, total number of bytes of data read from the main memory. How much of data is transferred from here into the CPU? That is first question. First number. Okay, you have to choose one of them. And then total number of cache lines or cache blocks written into. That means how many cache entries will be overwritten or replaced. Okay, that's the answer. So that is the second value. With this much of explanation, I want you to answer the question. Okay, let me launch the poll. Quiz 3. Okay, guys. Some people are answering correctly and then going to a wrong answer. I don't know. So please don't change your mind. In the exam also, you guys are doing that. I have seen, I heard also. Okay, while you are answering, let me help you. Okay, in the exam I can't do, let me do it here. See, as I told you, every block size is 64. CPU cannot read more than a block. Okay, that's one clue. And it cannot read less than that, because if it is asking for 4, it will get 64, because that's the purpose of cache. It cannot read 4 and it can't read more than 64. So you can now lock on to either one of this now. But how do you see whether this is correct or this is correct? I told you, if CPU has to access it, it should take it from the nearest cache only. It cannot take it directly from here. So whatever has been read by this cache, it should come here and then it should land here also. So I am sure now you know what is the right answer. Let me share the answer. You guys are not changing your mind. I don't know whether it doesn't allow or not. Okay, let me stop it. Okay, very good. Somebody is answering over chat. Okay, guys, this is the answer. Okay, still why are you thinking it is C or D? A is ruled out. Those 1%, please think about it. Even if CPU asks for 4 bytes, it will read always the block size. Cache is the purpose of that is this. Let me explain. If you are in a buffet, you are gone for a food, you have to go to the table to get your food. What do you do normally on a plate? Will you take only one item on the plate and come and sit on the table, or you bring multiple things on the plate and then come and sit and eat? Because you have to walk that far, you will normally tend to carry more food. How much ever you can fill in your plate, you bring it, so that you don't have to walk again to the table. So that's the same purpose here. Even though CPU wants 4 bytes, it has to go too far to go to the main memory to get it. So it will get always the block size of cache. So 64 bytes it will take. And then since all block size are 64, the same size 64 block is moved from the main memory to the cache. So the first 4 is not correct, and this is also not correct, because actual number of bytes taken from the memory is only 64. It's not 192. Don't think that one set of 64, another set of 64 byte will be here. No, it should be same 64 byte of data will be residing in all the caches, same copy of it. Because inclusion principle, you should remember, in memory hierarchy, every level should have that same data in it. So inclusion, it should be included in every location. So only 64 is the right answer. In that case, 1 is not right, only 3 is correct, because it is not enough if you copy and bring it to this cache. You should be here for the CPU to use. So 3 caches have to be filled. So number of cache lines blocks written into will be 3, and total number of block size moved from main memory is 64. Okay. Is it clear, guys?
Yes.
Okay. So if you want to read more about Core i7 cache design, I want you to read this. Okay, good. So let me now, the explanation is given here for you to read it later. I will not spend time. Okay, guys. Now quickly we will look at these categories. See, I will tell you one more thing. Initially, when the course is starting, I need to introduce so many new terms and concepts so that I can go into the detail. So it might be looking little overflowing or too much information, but if you have this information in the back of your mind, the rest of the course becomes easier. So I normally tend to give you overall view of the course and then go in detail into that. So please have patience. You will be able to appreciate and understand this. And I will explain any amount of time you want, any number of times. And I will ask questions so that you will be able to understand it better. Okay. Don't give up. Don't think that you cannot follow. You can. Even if you are giving wrong answers, don't lose your heart. If you have interest and to learn, to understand, you will be able to do. Okay. It's only your mind block. Okay. And you may wonder, why should I understand this processor architecture? I'll tell you, the amount of courses you have done, number of courses that you have done which are related to processor architecture is much more than any other line of ECE. Okay, you have not had many courses on VLSI design in particular. You have never not had too many courses on communication theory and fundamentals. So processor architecture is where you have spent a lot of time on. Embedded software is one area where you can get into, and you guys are all going to be out of college in another 4 months. So you have more opportunities to improve your knowledge on this area and to get a job in this area. Okay, basic programming skills if you have, and you understand the architecture and OS, computer organization fundamentals, you will be able to do either work in a company or start up something, or even training institutes you can run in your country. Okay, you can run Raspberry Pi training or Arduino training. There are so much of interest in the country. You can do all this. You can make money out of it. I'm telling you, I promise you, you have lots of opportunity, especially a developing country like Myanmar. So this is the area where you can actually shine and get into make money. So that is a motivation. I'm sure all of us are working for that. So please bear with me and listen to it. Nobody will explain in this great detail to you. So if you don't understand, ask me, I will clarify. Okay. Okay. Let me not give you more of blah. Okay. Single instruction, single data. That is ISA is instruction set architecture. So every ISA correspond to a processor family, and every processor family either falls into one of this category, either SISD or SIMD or whatever. So if you look at a processor which follows this category, which falls under this category, it will be executing one instruction stream at a time. And if it is an unpipelined CPU, that means it can only take one instruction into the CPU, finish execution, and then bring another instruction. Then it will be operating on one instruction stream and one data stream. Okay, it cannot be more than that. And a CPU could be implemented using von Neumann architecture in that, because I am saying it can do only one instruction and one data. It is, if it is a von Neumann architecture, it will be either fetching an instruction in one cycle or data in one cycle. It cannot do both because of the restriction in the construction of the CPU. CPU is connected to the memory through only one interface, and any program to execute, it should read a program first and then execute it. And if it has got only one interface, it can either do instruction fetch, or based on the instruction, it has to fetch a data. In another cycle, it has to fetch a data. So it can do one of it in a particular cycle. So this is a good example of that. You guys understand it better, very well. It's an example of non-pipelined architecture. So you know these registers. I have explained it many times. So it will use these registers and access it. That's all. This is a simple SISD architecture. Now, just I'm giving you the same example. It does not have any instruction level parallelism. Why do I say? Because it is executing only one instruction at a time. No, one more itself is not even inside the CPU. So there is no instruction level parallelism. Okay, in this particular design, please understand. And there is no data parallelism also, because it is operating on only one data at a time. Okay, don't get confused. It is taking two operands, so I am operating on two data. No, because if it has to do an add operation, it needs two data. So it doesn't mean that it is operating on multiple data. Okay, only when you do two different multiplication job on two different set of data, it's called data parallelism. If you are taking just reading two data, doesn't mean that it is data parallelism. Okay, I hope this is clear. So modern and recent SISD designs have concurrent processing characteristics. So this is a very limited implementation. SISD with this unpipelined structure is limited implementation. Suppose if you introduce pipelining, then multiple instructions will be in different stages of execution. I will talk about it in the next class. Even if you don't follow now, do not worry. So I am not expecting you to understand it right now. There are ILP and superscalar processors, which we will talk about it starting from next class. What I am trying to say is, if a CPU is fetching more instructions and then parallelly executing them on different stages, it is called instruction level parallelism, ILP. If a CPU has multiple pipeline structure, every instruction going through them in parallel, it's called superscalar. Okay, if there is a pipeline, more number of pipeline, it is called superscalar. If it is just one single pipeline, it's a instruction level parallel processor. So ILP is having single pipeline, superscalar having multiple pipelines. So inside a pipeline, multiple instructions will be there. So keep it in mind. Do not worry if you don't understand it fully. Okay, those processes also fall under SISD. Okay, that's all I'm trying to say. It is not that only unpipelined processor is under SISD. Even this and this fall under this category. That's all. This is a advanced implementation of SISD category of CPU. Okay, let us go. SISD is done. We'll come to SIMD. Now, what is the difference here? It is taking a single instruction, operating on multiple data simultaneously. That means in a given cycle, one instruction is fetched, and then in the next instruction, maybe they say instruction is operating on multiple different data. That is called SIMD. So I explained this in the previous class. Multiple processing elements are there. Each of them you can consider it to be one ALU. Not only ALU, one processor, a CPU. Each one of them is one CPU. Okay. So each one of them is getting the instruction and independently running on, operating on their own data, its own data. So SISD is a single core processor, whereas SIMD is a multi-core processor because multiple processing elements are there. So there is a parallelism because though they are all executing the same instruction, they are running in parallel. Imagine if there are 4 processors here, one add instruction is given. Okay, assume one add instruction is fetched. Then this add instruction is executed by 4 processors in parallel. But they are all operating on different data. If it is R1, 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 that R1 is here also, it is also here. A different register is here. So this add R1, R1 is operating on its own R1, whereas the same instruction is working on its another R1. So that is why it is operating on different data elements because they have their own register set and they operate on it. So this order operation is performed on multiple different data values stored in the registers because there are physically 4 register set. So, but all of them are executing the same instruction in the given CPU cycle. So SIMD is single instruction getting executed by multiple processors operating on different data. So it's a multi-core processor, but it has a limitation. Each processor can execute the same instruction. If they cannot, one cannot execute add at the same time, another processor cannot execute mul because they are given same instruction. That is the only difference. Okay. So these are all, you know, what is P, what is CU. If it happens to be a one item, is again, it depends on the implementation. Only instruction will be fetched in one cycle and data is accessed in the next cycle. Okay. So each PE executes same instruction on multiple data streams. The SIMD achieves data level parallelism. Why? Simultaneously, you are generating different data streams. You are operating on multiple data streams. So it's a data level parallelism. Okay. Graphics processors, GPUs, they fall under this category. Okay. Normally GPUs have multiple cores inside them and they all do the same job simultaneously. So let me give some popular example processors in the system, in the market. This was introduced way back in 2000 or even earlier than 2000. Yeah, 1990, if I remember correctly. It's called MMX extension. In Intel processor, they had introduced new instructions to operate on multimedia, that's audio or video data. So like floating point extension, multimedia is an extension. A separate processor was there and Intel came up with that. And AMD came up with some other GPU and HP, Hewlett Packard, they came up with another extension. So they are all GPU processors, graphics processor. And these CPU companies are normal microprocessor companies. They come up with a graphics core which will work along with the microprocessor. So if Core i7 or Pentium is running along with the multi-core processors. Okay, graphics processor, core. So multi-core processor with the one microprocessor and one graphics processor. Okay, they work together. All the graphics related instructions are executed by this. Don't have to worry too much about it. I'm just giving you overview. You should know this. So let me tell you what is SIMD. Another name for SIMD is vector processors because graphics is nothing but vector operations. Because pixels are arranged as matrices, the images are operated on by operating on a matrix of data. Okay, so imagine you need to multiply two vectors A and B to get C. If you have a SISD processor, that means it has got only one register set and only one CPU with one ALU. It has to do this multiplication, get the result, then another multiplication and get the result. It is called scalar operation. There is no vector operation involved. So SISD fall under this category. Now SIMD operation is a vector operation. Simultaneously, the all four data elements are multiplied and you get the results in the immediately in parallel. So if you can see, A1 and B1 is multiplied simultaneously with A2 and B2. So it's a data level parallelism. And how many cores are there? 4 cores are there, and they all execute the same instruction, which is nothing but a mul. So it falls under SIMD category. Okay, so this is how is it implemented. If you want to store a vector data, you should have a register set like this. Okay, one data here, and they're all physically, these registers are there, and they store different vector elements, and different 4 ALUs are there physically. All of them operate on different set of data and give the result back. So how do you program ALU? You will read the instruction and give the command to all ALU, perform mul operation. So all of them are getting the same instruction, mul, and they operate on different set of data, get the result. So this is how it is implemented internally. This is a good example of SIMD or a vector processor. How many cycles it takes? 4 cycles. Sorry, this takes 4 cycles, this takes 1 cycle. Okay, very good. I am explaining the same thing here. A simple implementation of SIMD is given with the 4 ALUs, Ps, processing elements. They all operate on a data vectors. All ALU perform the same operation. That's why it is called SI single instruction. But the data elements are different. That's why it's called multiple data. All results are produced at the same time. So you get a 4 times performance, because this was taking 4 cycles to perform the same operation, which is done in 1 cycle. So you get a 4 times improvement in performance. Okay. Now let us go into MISD. What is MISD? Multiple instruction, but single data. You saw car factory where the car is going through different stages and multiple instructions are getting executed. Multiple operations are getting done on the car. So how do you see it in a CPU? So let me, this picture you have seen already. So what do? We give a single data. Okay. So single data is, this data stream is single. It is fetched from the same element. The same data is going. Okay. Whereas different instructions are given. Both are shown in the same shared memory. Please remember, even our main memory in the CPU has both code and data, stack, everything together. So here also instructions are also stored in the same place where data is stored. These are all instructions and this is data. Some both are shared, put in the same memory. But CPU is executing different instruction at different point in time. Even during the same time, they are executing different instruction, but they operate on same set of data. Okay, that's all. It's, if you understood SIMD, is a different way of saying that you run different instruction on a same data. That's all. Okay. So many functional units are there. So one more thing, remember, there are different processing elements here also. This is also a multi-core processor, not like SISD. SIMD is a multi-core, MISD is also multi-core, because you need multiple processors, multiple register set to operate on to execute different instructions. Okay, though it is operating on same data, it has to execute different instruction. That means it should have different set of CPUs. Okay, I explained about fault tolerant systems. I will give you how it works with the example, so do not worry about it. A fault tolerant system have redundant processing. Okay, in the flight I told you that it will have redundant processors. In case one fails, other one will take over. Okay, so it is to detect any error as well as mask that error. Mask means suppress that error so that the system functions properly. So we normally have multiple fault redundant processing elements, so that one of them fails, the whole system does not come down. Okay, so another example I told you about network processor. Let me explain them with a picture in the next slide. Okay, don't worry, let us look at the picture. Okay, this is a fault tolerant system. You see multiple cores are there, multiple ALUs. It is getting an instruction input. This is not an instruction for that matter, it is a data input. Okay, in this case, let me clearly say whether it means, okay, it has got both different sensors coming in, and here input means, maybe I will change it, input gives you a confusion, I will change it to instruction. Okay, let me change it to instruction. Okay, then it is same. Okay, let me explain again. This input does not give you, does not show you that it is a data. Data is also coming in. Okay, sensor data is coming into the ALU. It is operating on the data the same set of algorithm. It could be to decide whether engine has to be, speed has to be increased or decreased, or in a flight control system. Okay, based on the sensor input, and it is giving some decisions at the output. Now there is a voter logic. What is the voter logic does? It does choose the majority output which are matching with each other. Suppose output is a single binary input output. If suppose the systems are giving 1 1 0, the output will be 1. Majority is 1, so it will be chosen. Now what does the 0 means? That means this ALU is not doing the job properly. There is some failure happened inside. Okay, so faulty ALU will be 3 in this case. So voter logic decides based on the majority of what it is getting. If it is two systems are saying 1 1 and other one is saying 0, it means it is something is wrong and these two are correct. You know, probability wise, two systems cannot fail simultaneously. That's what we are assuming. There is a possibility that both have failed and then this is only correct. We may be wrong, but we have to go by probability that only one has failed, other two are working fine. So majority is taken, and these are considered as the correct output, and this is considered to be a wrong output, and it will find out that ALU3 is faulty and somebody has to come and replace it. Okay, so that is what is a fault tolerant system. I hope this is clear. That's what I'm explaining here. Different PE outputs are compared and then the majority is taken as the correct output and the faulty one is highlighted. But most of the time you will get the same output in all three and nothing will be chosen as faulty. Everything is working fine. Only when something fails, you will see that there is a difference in the output. Okay, so this is how fault tolerant system work. And then network processor. I don't want you to worry about not understanding it. I will explain. I will try to explain. Even if you fail to understand, don't worry. This is the company which I worked on. More than 12 years I worked in the company. We had a network processor which is receiving packets, network packets. And they process, as the packets come in, they process the packet, find out whether the packet is corrupted and where is it routed, where it is supposed to go, and then send it across to the network port. Which port it is supposed to go, it will be sent. So the packet comes in, as you know, TCP IP, we have multiple layers of protocol. So even Ethernet. So for routing a packet, you have to look into IP and Ethernet. If any application specific information has to be seen, whether it is UDP or TCP, it has to look into TCP packet also. So a network packet coming in will have different headers. If you recall, Ethernet header here, IP header here, and TCP header here. So each of those units here run different programs. Okay, multiple instruction. It will running multiple instruction on single data. This is a single data, which is a packet. And one will be looking into Ethernet packet, Ethernet frame. One will look into, one program will be looking into the IP frame, header, and another one will be looking at TCP and processing them independently, one after the other. After all the processing is done, the packet goes out. It is similar to what happens in a car manufacturing assembly line. So that's all at a high level. I hope you will understand it because you know networking, which I taught you. So don't worry about remembering these names. It is a company Agere Systems proprietary names. This is what it is doing. Okay, they process the packet, and we use the different language called. I have not mentioned it here, I think. Okay, we program it using different language. These processors, it is actually running at the network speed. Okay, that's all it's required to you to understand. Don't worry about trying to understand more than that. Okay, any questions so far, guys? I should not keep going. Let me ask you any questions. All good so far? All of you are alive, awake, not sleeping? Okay, awake. Okay, I have brought some jokes for you guys for today. I will do it before the break. Okay. Okay, good. Thanks. So let me last implementation, then I will show you some. I'm sorry. Okay. This is the most complex implementation of all. Okay. Multiple instruction and multiple data is our laptops fall under this category. Okay. I'm sure all of you know that our processor is a multi-core CPU, and it is having multi-threading facility, and it runs different programs on different cores. So one core will be running a PPT, one core will be running a browser, one will be running a network protocol software. So they are all running different programs simultaneously. So they are operating on multiple data. One second, there is some question here. If they have multiple instructions, their working functions and goals are not same. How can the output be same in MISD? Okay. Okay. Very good question. So here it is used for a different purpose. Okay. Okay. Let me explain the question. What she is asking is, if there are multiple instructions and their working functions and goals will be not same. Okay. So let me explain here. Though we call it as multiple instructions here, we feed the same set of instruction. Okay. Then you may question, is it not same as SISD? Okay. Here we are giving a same instruction set going into the different ALUs. In SISD, what happens? There is only one ALU and one instruction stream going in. Here in a fault tolerant system, okay, not in this category. In this category, different instructions are going. Whereas in fault tolerant system, we are calling it as multiple instruction because there are multiple ALUs, there are multiple pipelines, there are hardware structures, which are capable of taking different instructions, but nobody prevents you from feeding the same instruction, right? It has got a facility to get instruction, but you can decide to give same instruction there. So what we are doing is we are using multiple ALUs for a different purpose here. Okay, and same data, you all agree, it is because the same sensor data is given to all ALUs, because at any point in time, a aircraft pressure and engine speed and its temperature and the fuel tank volume, everything is same. So in data is same, but we are deciding and we want to use it for a fault tolerant system. So we are feeding same instruction also, though it falls under MISD category, it is internally executing the same instruction. Okay. Okay. So ALUs are function to work different, implemented differently. Okay. In this case, let me tell you one more thing. All ALUs are identical. They perform same set of operation. They are capable of performing same set of operation. Okay. And all of them have same multiplier, same number of adders, floating point or whatever it is. They are all capability wise, they are same. If you feed different instruction, they will perform different job. But we choose not to give different instruction. We are giving same instruction. In the sense, different streams are there, but they are all feeding same instruction. Okay, in the fault tolerant system. Okay, very good. Good question. I want you guys once in a while keep asking. Okay, I may miss out some point. Okay, let me summarize what I have explained based on her question. A fault tolerant system, I said it is MISD. That means I said multiple instructions are coming, multiple different instructions are coming, and then they execute it on same data. Now, same data, there is no, the statement is correct, because in a flight control system, the data is same. We are feeding the same sensor data to all the ALUs. You are free to give different instructions to ALUs, but because you are using it as a fault tolerant system, you are having redundant CPUs in the system to catch errors. We want it to operate on same data as well as same algorithm. Okay, in that case we will be feeding the same instruction, but sometimes you may also run different algorithms and choose the best among them. Okay, that is also possible. If the decision is coming from different algorithms and we think that whichever is the majority I take it, or whichever is the higher value I may take it, that is also possible. But let us restrict to the one situation wherein we are comparing it and choosing it. So we will feed the same instruction here. Okay, so I hope this is clear. And okay, it is same as SISD except from having 3 processing units. You are right. Are you sending it to everybody? No. So I cannot copy, select all. No, I cannot copy. Okay, let me rephrase, tell the people. It is functionally same as SISD. Okay, because it is operating on single data. And I am saying that all of them are executing the same instruction. That means it is nothing but SISD. But it has got a redundant ALUs built into the system for fault tolerant purpose. Okay, that's all. So it is same as SISD. We are using MISD architecture to get the best result, a reliable result. That's all. Even if one fails, the system will not fail. In a SISD case, if that one ALU fails, the whole system will fail. Here, that is not the case. Okay, very good. Now let me go to MIMD. MIMD is the most complex thing I said, and it is parallelly running multiple instructions and operating on multiple data. And again, this is a multi-core processor. If you compare all the 4 categories, by now you might have realized that which is a uniprocessor and which is a multi-core processor. I want you to think about it. I will not tell the answer now because it's very obvious, but I will not tell it now. So MIMD systems can be categorized based on the shared memory being used. Now, let me give you some more concept here. Here we are using shared memory. We used earlier also shared memory in the SIMD case, wherein different instructions were, what did I say? Where did I use, one second, I'm going back. We use shared memory here also, wherein different instruction we used and same data was coming from one place. We use shared memory in MISD case also. Now let me come into MIMD. Here also we use shared memory. That means what? We use different DS and different IS here. So it is a multiple data, multiple instruction and multiple data. So it's a multiprocessor system. Each processor executes asynchronously different set of instruction. Okay, this is very important, guys. Now let me explain one concept. Single instruction, multiple data. We say that it is a graphics processor, GPU. It is executing the same instruction on multiple data. If I ask you a question, whether it is synchronous or asynchronous, can one of you or many of you can respond? Is this processor SIMD executing? It's also a multi-core processor, but they are all executing same instruction. I said, is it executing synchronously or asynchronously? What do you think? Okay, very good. Anyone else? Very good. If all
Synchronous.
are executing the same instruction, it will take same number of cycles. If it is a multiplication, it will take some 10 cycle or 15 cycle, or the division, it may take much more. So all of them take same number of cycles, and only difference is different data. Okay, you may wonder that if I use different data, will it take more time? For human beings, suppose if I divide 259 divided by 7 and then 5624 divided by 8, you may take different amount of time for division, because we are human beings. We don't process these numbers. We go sequentially, we keep dividing it. But as far as the processor is concerned, even though data is different, this element, the values are different, it is having a capability for either taking 32-bit of input or 64-bit of input and then dividing it. It doesn't matter whether you are giving a huge number within that limit or a small number, it doesn't matter. Whether you are giving all zeros or all ones, it doesn't matter. So it will take the same number of clock cycles, not like human being. Okay, I hope this is clear. If you remember how a multiplier or a adder is implemented, you will know that based on the data, it is not going to take different cycles. It is going to take the same number of cycles. So single instruction and multiple data will execute instructions synchronously. They will take same amount of time. That's what we mean by synchronous. Whereas asynchronous means here instructions are different. One CPU will be executing a mul, maybe another will be doing an add. Add will take much lesser time than mul. So they don't execute the instructions synchronously. So they are asynchronous execution. So this is one important point you should remember. Okay. Okay, good. So I spoke about shared memory in both cases. Let me change the color. I don't know where I picked up this color. So there are two different shared memory, single shared memory and distributed shared memory. So after the break, I am going to talk about these two. Okay. What is the difference between these two? Right now, assume that this shared memory can be either single shared memory or distributed. Let me tell you what I mean by this. If I say a multi-core processor is having a 1 GB of shared memory, I can decide to have all 1 GB in one place physically. Then it falls under single shared memory category. Or I can also decide to keep this 1 GB divided into 256 MB each. Okay, physically different locations. And suppose if I have a 4 cores, Okay, CPUs are shown as a cycle, and these are all memories. I may connect these processes together, whereas other memories are connected to a shared bus. Okay, let me explain with a picture later on. This is a rough picture. So I can distribute the shared memory of 1 GB on different locations. When I say different location means it is not connected to the same data bus in the same length. All different processes are not connected to the memory identically. They are distributed over. Okay, so we'll see that shortly. All supercomputers fall under this category. Okay, that's all. So we will take a quiz and then stop. Okay, I am sure you guys are waiting for a break. Let me see how fast you answer these questions. Okay. Can you guys quickly answer? We can take a break fast. It's all in your control now. If you want a break, answer fast. I am going to wait till at least 50 people respond. There are currently 36 people responded. Please give answer. It doesn't matter whether it's correct or wrong. Most of you are getting it right. Very good. 45 now. I am going to see who are all not answering at all consistently. Okay. Those guys are going to get some penalty. There are some 20 marks reserved for attendance. If you don't answer, that means you are not physically here. Maybe you are not even looking at the presentation. So I may conclude that those who are not consistently answering are not physically here. I may decide to reduce marks. That's the only way to. I consistently see 3 people, they log in and go off. They don't even sit in front of the laptop. I'll find out who are those 3 important people. Good. Okay. I'm very happy with the response. Let me share. Okay, from one of you, how many of you? Some few people have got it wrong. Okay, don't worry. See, may not be a multiprocessor when I say, that means sure, it is sure that they can be multiprocessor, but may not be multiprocessor. Other things, that means that other categories need to be implemented with multiple processors in it. Okay. If you recall, SIMD is what? It is taking the same instruction and operating on multiple data simultaneously in the same clock. That means it has to be a multi-core. It's very simple. Wherever you see M, they need to have a multi-core in it. Only this guy doesn't have a M in it, so it is need not be having a multiple processor. This M and this M actually correspond to each other. So I'm not saying you go by that. Logically, if you think, only this can be implemented with a single core, but I can't implement any of this with a single core. That's all. So that's the answer. I hope you got now. If you don't still understand, no problem. You please ask me. Okay. Now let me. Did I stop sharing? Okay. Okay, guys. Answer is B. Very good. Now one more question before the break. Please write it on a paper. You may get it wrong. So I want you to order in this way. Is this correspond to this or not? Is this correspond to this or not? Let me reveal something to you so that you can think about it. Wrong answers are more than the correct answers. Please think again. Something is not matching. I don't know why you guys are getting a. Okay, let me tell you something how to read the picture. If a line is coming like this, it is the same instruction. You can see that it is connected, okay, like an electrical connection. Same voltage is coming to all the places. So if the connection is like this, it is a S. If it is like this, it is M. Okay. Different lines are connecting to the PE. If it is like this, it is yes. Can you now relook to your answers? Are you not able to change the answer once you decide? Okay. You guys are not changing your answers. So let me stop the polling. Share the results. Okay. So why did you get it wrong? Why many are giving C? Is MISD? Is it MISD? Instructions are correct. It is M. But data is not, yes. Data is different. Data is given to different elements. So SD is not correct. How did you say this is MISD? 22 people. Why did you say this is MISD? It is SIMD. Not even SIMD. It's MIMD. Okay. This is MIMD. So let me stop sharing. You guys are waiting for the break. I am also waiting. Okay. This is MIMD because let me see. Okay. This and this are two different instruction set. Okay. Maybe this, some of them are getting same, but there is some difference here. These two are different. Similar to what I mentioned to you in the fault tolerant system, I may decide to give the same instruction if I want, but connect or if I have, as long as I am able to feed two different instruction in the physical construction, then it will fall under MIMD. Okay. So you may be confused, might be confused because of that. This is very clear, SISD. Here I am able to give two different instruction here. Okay. So it falls under MI, and data anyway is multiple, so MD. Okay. Here single instruction only. I cannot, even if I decide to give different instruction, I cannot do. So okay, one more thing you let me clarify. The physical construction decides what is that you are doing. Okay. In terms of instruction feeding, here I may have multiple instruction feeding capability, MISD capability I have, but I can decide to give same instruction also. So that is coming as a software. Hardware, there is a limitation. I cannot change it. As long as I have a configurable hardware, I will not be able to change it. Similarly, here I will, though I am sharing, giving the same instruction, there are two different feeds are there. So it will fall under MI category. Okay. Okay. Shall I stop here?
Yes.
Yes.
Sir.
Okay. 10 minutes from now. What is the time now? 20 to 20, right? 2:30. Okay.
Yes.
We'll meet at 2:30. Bye bye.
Bye bye.
Come back. Welcome back. Let us spend some time now, half an hour or so, on shared memory, different types of shared memory. This is a very simple topic. Once you understand the concept, it's easy. So let me explain this picture first. This is a processor. All the circle what you see is a processor, and the rectangular one is a memory. Now, if you see here, this picture, let me take the pen now. If you see, this memory is directly connected to the CPUs. All of them are close to the memory. They are all connected by a same bus. You know, physically they are all connected through a same bus. So because they are directly connected, it's also called tightly coupled system. Tightly coupled, tightly coupled with the memory. And since all processors are directly connected to the memory, the same way, all of them are equally able to access any location. Equally able to access, what I mean by is, all of them take the same number of cycles, same amount of time to read or write into the memory. They don't see any difference. Suppose this processor is accessing one location here and other processor is accessing some other location here, they will take the same time. In the terms of number of cycles taken for read or write will be same. This is called a shared memory, just a shared memory, and also it's called tightly coupled system. Now, let me come here. Okay, let me not here. Sorry, let us come here. These two are more or less same in terms of logical operation, but physically they are different. Let me explain that. Now, what is this shaded portion? This shading. If you see this, this shading is same in all places. Okay. That means they all belong to single address space. Address space. What I mean by that, suppose a memory, this address 100, okay, this is address 100 is located here, and address some 500 is address 500 is located here, maybe 400 is here and 200 is here. They're all same logical, they are physical memory, but their addressing is same. That means if a processor, this circle is all different processors, they are executing different code, but they may access the same location in the memory, same address. Suppose this processor is giving out an address 100, that 100 will refer to a location in this place. It will be same for every processor. The 100 address is here physically. Similarly, 400, if anybody wants to access, they will access the 400 location located in this physical memory. So they all come under single address space. That means within the address space, what I mean by same address space means an address in an address space, they correspond to the same location, whatever may be the physical location of that. It could be located somewhere else physically, but if a processor is giving an address, it will come to that location. That is the single address space. Okay. So now I said this is 100. This processor may access location 100. In that case, because it is directly connected, it will access it in a shorter number of cycles, maybe 10 cycles. Suppose this processor can access it in 10 cycles, but if the same address has to be accessed by a processor here, it has to go to this and through this interface and access the memory. So it is not directly connected location. It is physically somewhere else. So that same address 100 for this processor will not take the same number of cycle 10. Maybe if you say this is introducing a delay of 10, another, this is introducing another delay of 10, then it directly, it has to go through this CPU or maybe some physical interface. In that case, it will be at least 20 plus. The access time will be 20 plus number of cycles. So every location in the shared memory, if it is distributed physically, it will not be taking the same number of cycle for all the processor. They will be taking different number of cycles based on where exactly that location is physically there. Whether it is directly connected or it can be reached with one interface, or it has to be reached, no, it has to be reached with the two interfaces. It depends on the distance, physical distance between the processor and the other one, and the link speed, all that will come into the picture. This is called distributed shared memory. So now what is the difference between these two and this? You can see from the picture, the shades are different. That means these two memories fall under the same address space. These two memory fall under another different address space. When I say address space, that means given an address, whether it is physically pointing to the same location or not. Now, if I say this is a shaded memory and this is another one, yeah, address 100, if you are accessing this address space, let me address space 1, this is address space 2. If a CPU, any CPU may access the address space S1 and address particular value 100, then it will refer to this location. Suppose some other CPU is trying to access this address space, which is one of this, and the address is 100, it will be physically different location. The values will certainly be different or maybe same, but it is physically different location. So these two address spaces are different. Same way, if in this address space, some two processors are accessing the address 200, they will come to the same location. Okay, it depends on which address space it is pointing to, which is addressing it. So they are all physical memories, no doubt about it, but they may have different address space. That means they will be mapped to different address spaces. In that case, an address some X here will be different from an address in this location because they are physically different memories. And then on top of it, if that address is it directly connected or is it little away from it, based on that the access time will be different. So there are another complication here, whether it is the same address space, and then if it is same or different, whether it is directly connected or little away from there, in that case the access time will be different. So that is called distributed memory. So let me summarize it again. Here you should be able to understand it clearly. A shared memory, if there is a word shared is there, that means one single address space is shared between processors. That's all. If this word is there, it means that one address space is only there in the system. If you see, this also only one shaded region is there. Here also one shaded region is there. That means it is shared. One address space is shared between processors. And if additional word distributed is there, then that shared memory is not located in one place. It is distributed over different physical locations. So once I give you the name, you will be able to imagine whether it falls under this category or this category. Now look at this thing. There is no word shared. That means the address spaces are not the same. It may be same or different. It can be different. And don't assume that it has to be only two. There may be any number of address spaces. Maximum maybe 4 address spaces can be there in this system. But if I have more number of processors connected to different memories, any number of address spaces will be there. So distributed memory means it is physically distributed. It is not here. It is not in one place. Memory is distributed. and there is no word shared here. That means it is not a single address space. It can be more than one address space. That means if I give you address, it is not enough. I have to tell which address space I am referring to. Based on that, you have to go and access that. Okay. So why are we talking about all this? Because we are talking about multiprocessors. Except SISD, everything else is multiprocessor. In that case, you have an option of either having the memory distributed or in physically one place, and it can be either one single address space or multiple address spaces. And one more thing you remember, when we speak about memory, we are always referring to the main memory, not the cache memory that you see inside the CPU. So there are multiple cores. I told you there are multiple cores and then different levels of caches and main memory. This memory refers to the main memory, not the cache memory. If we are referring to cache memory, we will be specifically saying cache. If there is no cache and if it only says memory, it is the main memory. And if it is saying distributed, this main memory is divided into multiple blocks and distributed over different places, then it is this. Okay. If it is just a shared and no distributed, it is physically in one place. All the processors are connected directly. Okay. I think it is clear now. I hope so. Let me now run through the slides, which will be useful for you to read through it later. Okay. Shared memory is a system composed of a set of processors and a single physical memory. Set of processors and a single physical memory. This is shared memory. Very good. Very clear. They all operate on the data belonging to the same address space. There is only one shared location. There is nothing like I divide this into one shared and this is one shared like this. No, we say that they all belong to one address space. So any address 100 or 200 means one particular location. There is no ambiguity there. So this also you understand. Now, what is distributed memory? We are talking about this. A distributed system, memory system, each processor has its own local memory. I call this as a local memory. This memory is a local memory for this processor. This is the local memory for this processor. Having separate address spaces. That means the one is hashed, one is some gray colored. Okay, so its own separate address spaces and direct access to the local memory. The local memory is directly accessed by the CPU. So this CPU can access this memory much faster than this memory. Okay. This CPU, okay, let me, too many lines. If I am saying that this CPU is accessing a location here and another location here, this will be accessed much faster than this because it has to go through the link to access it. Don't think that CPU will be disturbed. This CPU is accessing this memory, this CPU will be disturbed. You might have heard about DMA. I said about DMA, direct memory access, sometime in, I think in computer organization course or OS course, I don't remember. CPU will not be involved most of the time. Okay. This CPU can directly access the memory with the hardware interfaces. Don't worry about it. Let us not bother, but it will take more time. Access time will be more. So local memory is this, remote memory is this. Now, direct access to the local memory of a remote processor is prohibited. So if it is, if suppose it is not always true, sometimes it will be, if it is running different processes and it needs, it is to be protected, then it will be prohibited. Okay. So let me explain what I mean by this one. Local memory is having a separate address spaces, and direct access to the local memory of remote processor is prohibited. In the sense, there should be some control mechanism involved. Okay. Maybe the CPU, some OS will be running and it will be giving a specific access permission to access it. Okay. I'm not saying that CPU will be involved, but the OS running on it will be notified. So any operating system running might give a special permission that any process running on this processor will be allowed to access it. Without that, it will not be allowed. Okay, that's what it means by directly accessing it by a remote processor. So don't take it too much into heart, this statement. Okay, so distributed memory, you understand, it is distributed over different locations and local memory is there, and any remote processor wants to access some memory, some permissions have to be given. Directly you cannot go and access it because of the security reasons, privacy reason. And address space is also different. Once address spaces are different, it will not be possible for any process to access it. It should be shared, through some mechanism, other different mechanism. Now let us come to distributed shared memory. We are talking about this. The local memories are components of a common global address, because there is nothing called, there is a word called shared here. So the memory is shared across different physical location. That means it is a common global address space. This address space is common in all the places. So we are having different local memories. As far as this processor is concerned, this is a local memory. This processor is concerned, this is a local memory. But they are all component of a single address space. And any processor can access the local memory of any other processor. Now, this processor can access this memory without any access permissions. It can directly access. Only thing is, it will take more time. You cannot reduce the time taken. It has to be taking more time compared to this processor accessing a location in this memory. Okay. I hope you understand the differences between them. Let me explain some more details. Then we'll go into the more explanation. Okay. So shared memory holds data and code of parallel programs running on processors. See, let me explain this. Once I say shared memory, that means multiple processors are accessing it. And I'm not saying whether distributed or not. It doesn't matter. Distributed means it will take more time, but shared memory means multiple processors are involved. It is shared between multiple processors. So it can be holding a data or code. Okay. Do not assume it's only code or data. It can be both. And parallel programs are running because it is accessed by multiple processors. It is shared between multiple processors. So there should be some parallel programs running, because when you have multiple programs, they will be executing, when you have multiple processors, they will be executing multiple programs in parallel. So parallel programs will be running for sure, and they will be accessing the shared memory. Remember that. Regarding the way in which main memory is organized, as I told you, it is not a cache memory. Once I say memory, it is a main memory. It's organized and used by processors in a multiprocessor system. We divide it into two. I told you main memory only we are talking about, and I'm sure we are talking about multiprocessor because we are talking about shared. So either it is a shared memory system or distributed shared memory system. Either that physical memory, which is happens to be a main memory, may be in one place physically like this. Where is the picture? Here. Or it is physically located on different places. If it is distributed over different places, we call it as distributed. And if it is in one single location, we call just shared. Because we are saying shared because multiple cores are going to access it. And we are not saying distributed because it is located in only one place. Okay. I hope this is clear. Let me come to this sentence, this SMP. This is a very important acronym that you hear in processor architecture. Okay. and NUMA. Okay. Let me explain. In a shared memory system, the memory accessible to all the processors is physically at one place. Yes. And all the processors have the uniform access. The link connecting them is almost of same distance. That is why uniform access time to all the memory location. Remember, whether you are accessing a first address or the last address, it doesn't matter. Whether this processor is accessing or this processor is accessing, there is no difference. It will have same uniform access time. Okay, because physically they are on one place and it's a random access memory, so it will have the same access time irrespective of the location of the memory. So it doesn't matter which processor is accessing which location, it will see the same number of cycles to access it. And it depends on who is, whether any other processor is accessing it or not. Suppose if this processor wants to access the memory, it has to use the same physical bus. If already there is a transaction going on, it has to wait. So it will take more time. It depends on who has come first. But physically, they are all in the equidistance from the memory. Okay. So remember that. That is the reason. So if multiple processors are connected to a single physical memory and all of them are of same address space, then such multiprocessor system is called symmetric multiprocessors. It's a SMP system. That means these CPUs are accessing the same shared memory, the same address space, located physically in one place, having an uniform access to any location in the memory. Then these processors or the whole system is called symmetric multiprocessor system. That means they have the same kind of access time, either read or write or any location in the memory. So if I have to ask you, define an SMP, is a symmetric multiprocessor system having a access to a single physical shared memory and all the processors having uniform access time to any locations in the memory is the definition of an SMP system, which is given here. Now let us look at this picture. This place, don't get confused with this block. This is not a physical memory. It is saying that it's a layer, distributed shared memory layer. It's like an abstraction layer. Actually, physically, these memories are there. Okay, they are all connected through these interfaces. Please, these are all physical connection. These are all physical connection. What you see here is not a physical connection. We are just saying that they all fall under the same shared memory layer. That's why that picture is shown. Okay. Now, if you see this, it is a distributed memory because it is located at 3 different places. And this CPU is having it's a local memory for it. This is a local memory for this CPU and this is the local memory for the CPU. But it is a shared memory. That means they all fall under the same address space. That means if I hash it, I will hash on all of them same way. So if suppose this CPU is accessing a location address 100 and it happens to be here, it will have to come through this interface and then access it. Similarly, if this is accessing a address 100 that will also refer to the location here, and it has to come through the interface, this interface, if you can see this, and then this interface and access it. It will take different time, doesn't matter, but it will access the same location because it is a shared memory, and it is taking more time or different time based on the location because it is distributed. So a distributed shared memory is a non-uniform memory access. Once the memory is distributed, it will not have a uniform memory access. What I mean by non-uniform? Non-uniform from the perspective of the CPU. CPUs cannot access the memory uniformly. You cannot say any location in the memory can be accessed with the same uniform access time. Let me take an example. Suppose this is a CPU wants to access some location in this memory physically here in this address. It will access it fast. Whereas if it has to access here, it may take some time. If it has to access here, maybe it will take some more time based on the distance. Doesn't matter. It is not going to be the same like this location. So it is not a uniform memory access. It is going to have a different access times. So a distributed shared memory architecture will have a non-uniform memory access. So it can be categorized as is a non-uniform memory organization, access organization. So NUMA is one way of categorizing distributed shared memories. Okay, so I am introducing too many words: distributed shared memory, and non-uniform memory access. But if you understand the concept, it's the same. It's easy to understand. And I'm not saying it is same. It is easy to understand. One thing is, when you say shared memory, you should immediately remember, there is multiple cores. There are multiple cores, and they are sharing some memory. Either it could be a shared memory physically located in one place, or distributed shared memory physically located in different places. Either it could be, in this case, it will be a same address space. Distributed shared memory means distributed, but it is same address space. If I remove this and I say distributed memory, then you have to remember it is a different address spaces. So they belong to different address space. It is not same address space. That's a key point. Okay. So let me now show you this. Non-uniform memory access. That means what? Different processes are there. They're all connected to different memory modules. See, this is one module, this is another module, okay? Separate physically different modules, and we have put it together to say that they're all memory modules. So this is not a physical boundary, logical boundary, but these are all physical boundaries. They all have a separate interface, a bus running, a cable running between a memory and this, and similarly some cable running between the processors. So internally these processes will have cache memories. Don't think that for every byte it will come here and access. One more thing, maybe it is not worthwhile to have it in mind. If you have a distributed multiprocessor system, do not think that the processors do not have a cache. Don't think they will not have cache. They will have caches. They need to have, because inside the processor, the CPUs are there. They are running at a much faster rate. They need code and data available in their own local caches. It cannot come to the memory outside for every byte. So you have to default assume they have cache memory inside. Okay, because we are talking about a multiprocessor system. in that case, we cannot say that a processor doesn't have a cache. That's very illogical. Okay. So right now, maybe 20 years back, we may think that anyone may not have a mobile phone. But now in this current situation, we are assuming that everybody has a mobile, everyone has a laptop, everyone has a data connection, and all of you should be ready to take a class online from home. So that is the assumption. So similarly, currently these processors will have cache inside them. They will be able to access multiple memories. That's what we are assuming. Okay. So now NUMA means non-uniform memory. This is non-uniform memory and this is uniform memory. In that case, because all of them are located here, little bit of distance, and if you see the time taken for this processor to reach this memory, it has to go through this interface and this interface. So that's why we are calling it as a uniform memory access. And this network will make sure that anything is connected in parallel. As long as two processors are not talking to two different, as long as they are talking to two different modules, they can go through, the communication can happen. So we call them as uniform memory access, though they are all in some place. Okay. If I show you this picture, and then an interconnect network is a physical interface which is capable of, like a telephone exchange. It can connect this in and this for a moment and then disconnect it and then connect this with this. So based on the address generated, it will know that it is either belonging to M1 or M2, and then it will route the access to this. Okay, it's like a network access. Memory access is happening like a network access. Okay, you want to imagine like a packets going through network. Actual memory is being accessed using a network. Okay, little bit higher abstraction, and they share a single virtual address space. That means an address here is unique, and you will, if any processor accessing an address 100, it will come to the same location in the memory, same virtual address space, single address space. Okay, it is a single address space, but physically they may be UMA or NUMA. Okay, non-uniform access or uniform access. Okay, if it is all in one place physically and then they all connect through an internet network, it is a uniform access. But if you divide these memory blocks and then put it all in different locations, even then they are all single address space, but they will take more time based on where they are coming. Okay, if this processor is accessing this memory, it will take more time. If it is accessing this, it will take less time. Okay, so it may even access directly also. It may not come through interconnect network. It depends on the way it is connected. We don't know until we know the definitions and how it is done. Most likely it will be accessing it directly. This interface is provided for this processor to access any memory. Okay, it is supposed to access any of this. Similarly, this interface is provided for allowing this processor to access it. Similarly, this processor to access it. So these interfaces are required for that purpose. Okay, and they all fall under single address space. That means any location here will be unique, and there won't be a location 100 in multiple places. It will be in one place. Okay, that's all. So distributed shared memory is also a virtual shared memory. It falls under this category. Note that from the point of view of physical construction, distributed shared memory machine where very much resembles a distributed memory system. Okay, as far as the shared memory system concerned, either distributed or shared, they fall under the same category. Only thing is, distributed means the access times will be different, but address spaces are same. As long as the virtual address space is same, address spaces are same. That's all. Now let me talk about SMP. It falls under MIMD. Okay, this is one good example. One physical location shared memory is there. Different processors are there. As I told you, they have their own caches. Okay, there is no local memory. If there is no local memory, this L1, L2 caches are not same as local memory. Remember that they are not local. They are local cache memories. If you have a physically another memory, I call that as LM, then it is a local memory. Cache memories are not called local memory. It is a cache memory which is there within the processor. So it has to access this only for everything. Similarly, some IO is there. That's all. So everybody has same access time. All of them have the same address space. It is called SMP system, Symmetric Multiprocessor system. So they have their own ALUs, their own registers, their own cache, individual CPUs. They share a memory and physically in one place. Okay, very clear. An attractive feature of SMP is that the existence of multiple processors is transparent to the user. Okay, what I mean by transparent means, suppose an operating system is running. Okay, it has to be running. It will be running on all of them and they will be coordinating with each other, and they will, the OS will make sure that which process will run on which core, and you don't have to worry as a user whether my process is running on this processor or maybe both. You don't have to worry about it. At this moment when you are running your laptop, you don't know whether your PPT, no, you are not running PPT, you are running a browser. On top of it, our Zoom is running. Our Zoom software, either it is running on core 1 or core 2 or core 3, you don't care. You don't worry. At this moment, maybe it will be running on core 1. Maybe after some 10 minutes, it may be running on core 2. It is done by the OS. Transparent to us. We don't know. That is called SMP, Symmetric Multiprocessing System. So operating system takes care of scheduling the threads or processes on individual processes. We don't have to worry about it. Okay, that is the job of a SMP enabled OS. This is the job of OS to take care whether Zoom is running on this core or another core. And for some time it may be running, later on it may decide to run it on different core. That is OS decision. Okay, that is called an SMP system. So let me explain it again. SMP can be defined as a standalone computer with the following characteristics. There are more number of similar processors. The cores are similar in nature. They have similar capabilities. These processors share the same main memory. They all share the same memory. They all share the same IO system. All processors share the same IO. All processors can perform same type of functions. They are called symmetric. So all processors access the same display. All processors access the same mouse, same hard disk. So IO system is same. Shared memory is same. Whatever 4 GB or 8 GB you have, it is only one shared memory and all your cores are running and accessing them. So our system, our laptop is a SMP system. The system is controlled by an integrated OS. That means OS running on this and this and this are the same. Normally, what happens is OS will be running on one core, partly. Okay, as I told you in the OS course, OS is not running always. It runs whenever it is required. So it may be running on one core. Some part of the OS may be running on other. It depends on the implementation. Don't worry about how it is running. It is taking care that any process running on different cores are properly done. So this is an example of a MIMD system with a shared memory, not distributed, and having a single address space. So it is a physically single shared memory and multiple cores are using it. It's called SMP system. That's all. So I have come to the last slide. Clusters. Cluster of processors is called a cluster. Each is called a node. Now they have distributed memory. You can see this memory is here and memory is here. So this memory is a local memory as far as these processors are concerned. These are all processors. Whereas this memory is remote to this processor. And I did not mention a shared here. Okay, I didn't mention shared, only distributed I mentioned. I am not saying shared. That means This is a different address space. This is different address space. So if a processor is accessing a 100 address 100 here, it may be here. Similarly, in this address space 100 will be somewhere here in this memory. So it has to come through this link and then come through the link to access it. It has to come through this. Okay, that is the path taken. So it is a cluster of processors operating on different distributed memories. So let me explain with one slide. An important relatively recent computer system is clustering. Clustering is an alternative to symmetric multiprocessing. It is not symmetric. What is running here will be totally different from what is running here. And they are called clusters, a group of interconnected processors. And one system is called a whole computer and they are connected. Okay. So each is called a node. Whole computer means a system that can run on its own. This can run on its own. This can run it on its own independently. Even if this is disconnected, they will be running without any problem. But if they need to access it, they need to have a connection. That's all. So that is a clustered. Another name for this is distributed computing. Okay. So let me give an example in this current scenario. My laptop and all your laptops are distributed now. They are all clusters. We are all running different, even though we are all running Zoom on our system, what you see on my screen is different from what you see on your screen. And suppose our connection between me and one of your laptop gets disconnected, other systems still run. So actually, we are running an online class using an MIMD clusters of distributed system. So if I need to access your local memory, it will be different. Your Zoom software on your laptop is different from my Zoom software running. It is accessing its own local memory, whereas your Zoom software is accessing your own local memory. So the current system is a cluster of clusters, is a distributed system, and each of your laptops, my laptop and all your laptops, is a node. Okay, and we are all connected through a network, internet. Okay, so let me stop with this class today. Now we will stop the class with 2 quizzes quickly. Can you identify whether this system what is shown is an SMP or a cluster? Okay, very simple. I'll start the poll immediately. 6 launch. A lot of people are very happy that class is ending. Very good. Fantastic. Please answer quickly if you want to go and relax. I know you are relaxing already. Fast, 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 fast. 20 out of 52. You should not take more time. It's a shared memory. Okay. It is not distributed. And there are multiple cores, so you cannot say it's a multiprocessor system. Please change your answer if you are giving a wrong answer. It is a multiprocessor system, but with a shared memory, and it is not distributed because the shared memory is not distributed over different places. So don't get confused with the disk controller. Okay, disk is different from cache memory and shared memory. Memory means main memory. Okay, always the RAM. 30 people, 40 only responded. Another 10, they have you vanished or are you there? Okay. Shall we stop now? Only 45 responded. Okay. Guys, it is a share. A is the right answer. It's an SMP. Okay. Very good. But I am not very happy with the 70% answer. I don't know why 7 people are still thinking it is B. It is not distributed. Please remember. Don't get confused with this one. And then don't think that if it is not local, it is distributed. No. If it is not local, doesn't mean that it is distributed. If there is a memory, only physical one memory is there, it is called a symmetric multiple system, and it's not called distributed. Only when memory is distributed over multiple places is called distributed. Okay, maybe you may get confused because of that. Okay, Now let me launch. Okay, I have to ask you the question now. Okay, guys, last question for the class. I am sure you can answer it without even thinking. Please answer without thinking. Okay. See here, memory is here also, here also, here also, and it is all over network, and they all shaded same. There is no difference in the shading. So it is a shared memory, same address space, and it is distributed. Multiple processors are there, so it's not a multiprocessor system. So I have given the answer. Still 34 people only responded because I have given the answer. I don't want you to respond now. So good response. Okay. One question. Do you want me to share some jokes or not? Or you want to go home?